Good evening. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office, and it's my pleasure to welcome you to the Teaching Nano and Emerging Technologies webinar series. By teaching nanotechnology now, teachers are preparing students for the future. Nanotechnology can provide exciting examples like invisibility cloaks and gecko-inspired climbing gloves to inspire students. And nanotechnology is already impacting a broad array of industry sectors such as consumer electronics, textiles, aerospace and automotive, biotechnology, and medicine. And now I'd like to turn it over to my colleague Quinn Spadola, who will be your host for this evening. Quinn?
Hi, Lisa. Thank you very much. Thank you, everyone, for joining us this evening. Before we get started with the webinar, I just want to point out a couple of things happening here at the NNCO. Lisa just mentioned the Teaching Nano and Emerging Technologies network. If you're interested, you can follow that link to learn more or email us at the bottom at nanoed@nnco.nano.gov. Basically, we want to bring you together so you can learn from each other. And as a part of that network, we have the Teaching Nano and Emerging Technologies webinar series. We've had 3 previous webinars. Tonight is our 4th, and the last 3 are archived on NanoTube, the National Nanotechnology Initiative's YouTube channel. And this one will be posted as well, so you can certainly check out our past webinars if you haven't already. There's also a resource portal I want to point you to. There's over 400 resources on this portal that you can search by grade level, activity, etc. Please check it out. They're all designed to help teach nanotechnology in the classroom. And lastly, I just wanted to point out that our office provides for free Big Things from a Tiny World, which is a brochure to help introduce basic concepts to nanotechnology. You can either email or go to the webpage there to download it. So there's lots of great resources out there to help teach nanotechnology in the classroom. And always feel free to email at nanoed@nnco.nano.gov. One last thing I want to mention before we get started. National Nanotechnology Day, which is October 9th in honor of 10 to the minus 9th, of course. This is a community-led event to celebrate all things nanotechnology. Previous years, teachers have participated by having their students run the 100 billion nanometer dash, so 100 meters. It's a great way to get your kids outside and running around and also kind of help them realize how small the nanoscale is. So again, if you go to that webpage, you'll learn more. And if you decide to participate, please let us know. We like to keep track of what's going on, and we'll put it on the map of the various activities that are happening around the U.S. for National Nanotechnology Day. And the National Science Foundation and the NNI are, for the 3rd year, hosting Generation Nano, Superheroes Inspired by Science. This is a competition for high school students. They create science-enabled gear for an original superhero. They get to make a comic or a video. And the finalists are brought to the USA Science and Engineering Festival in Washington, D.C., which is awesome. So I wanted to let you guys know about that as well. And there's the link for that. Now, we're going to get to the main event, tonight's webinar, which is Introducing Nanotechnology into the Chemistry Classroom. And it'll feature Sherri Rukes, who has been teaching for over 20 years and is the president-elect of the American Association of Chemistry Teachers. I got to see this presentation when she was at the National Science Teachers Association annual meeting last spring, and it was wonderful. I thoroughly enjoyed it, and that's why I invited her to speak to all of you this evening. So, Sherri, if you're ready to go, I'm going to turn it over to you.
Thank you, Quinn. So, my name is Sherri Rukes, and I am at Libertyville High School. For the people who don't know where Libertyville is, I am the same distance to Milwaukee, Wisconsin as downtown Chicago. So I am very close to the border of the Illinois-Wisconsin line. So I'm here to talk about what I do in my chemistry classroom to introduce nanotechnology. And the first thing I'm going to ask is, if you look at these 2 pictures, how are they similar? For my students, when I show them these pictures, they first go, there's nothing similar about them. There's medieval times, it's unsanitary with the medieval picture, they're glass blowing, they're constructing. And then on the other side, they're like, it's a clean room. It has high-priced scientific equipment. It has people doing research. Those are the scientists. And then I tell them they're both nanoscientists, that they are both using nanotechnology. One may not know it, while the other one is truly trying to advance our science endeavors by nanotechnology. And so these little intriguing pictures and ideas I bring up in my classroom is how I get kids excited and start thinking about those areas. So the first question is, what exactly is nano? It's basically all around us. If you look, my students, I try to introduce pop culture everywhere, and they read books, they watch movies, and back in 2002, William Dafoe was actually a nanoscientist in the Spider-Man movie. Then in one version of The Incredible Hulk, you had him being created due to nanotechnology. And those were in the 2000s. Way back in 1966, you had Fantastic Voyage, where they talked about having these machines that go into the body to try to help us out. Back then, that was amazing. That was futuristic. Now, in 2005, GE actually had a commercial showing the same type of idea. And in fact, later on, CNN interviewed an inventor who came up with nanobots that would go inside the body and try to repair bones, repair things to help us out. So what used to be futuristic is really coming to life. And even in books, Michael Crichton talks about this autonomous gray goo that self-replicates, another form of nanotechnology. So by the definition, nanotechnology is the engineering of functional systems on a molecular scale. It is the intertwining of the sciences, because the physics, the chemistry, the biology at the nano level is different and unique, and we could help each part, each department out and further their discoveries. If you look at nanoscience, that is just the study of atoms, molecules at that nanoscale level. So why is it a big deal? Once again, we see these images. I'm sorry I couldn't show you the true IBM picture I wanted to, that IBM put out in magazines and on TV. They were able to manipulate atoms and write out IBM. And NIST did the same thing. All of these going to that atomic level will change the properties and give us fascinating new items. So one of the easiest things you could do in your classroom is just make sure you talk about the nanometer when you talk about the metric system. So how big is really a nanometer? Well, if you look at a bike is about a meter in length. Then if you look at the original iPhone, that's about 1/10 of a meter. You have then a ladybug that is a 1/100th of a meter, and a grain of sand, which is 1/1000th of a meter. These are all visible to the naked eye. We could see these things. When you go even smaller, for instance, the picture of the frog red cells, those are about 6 to 8 micrometers. 1/1,000,000th of a meter. That is a micrometer. If you look at a human hair is about 17 to 181 micrometers. If you go even smaller, you get viruses that are 3 to 50 nanometers, atoms that are less than a nanometer. In chemistry class, we talk about the allotropes of carbon, and you may bring up the buckyball, you may bring up nanotubes, and all of those are approximately about a nanometer in width or length. DNA is 2.5 nanometers. So there are many things that we use in chemistry and biology that are at this nanometer scale, but we never really focus or show the kids exactly how small a lot of those compounds are. So what happens to things at the nanoscale, and where can I put them in my class? Well, at the nanoscale, it's all size dependent. For instance, chemical properties, the reactivity of certain elements, compounds, really take off and change from what we see in the macro world. Thermal properties, melting points, change, mechanical properties, how adhesive or cohesive these compounds are. How does light scatter? All of these things give us the abilities to make new applications on this technology. In my classroom, I teach a traditional chemistry class. In honors chemistry, I teach the whole book. Here are some of the big ideas. We do bonding, which includes intermolecular forces, electrochemistry, rates in equilibrium, thermochemistry, solutions. All of these topics I have on the screen, I have activities that will show where nanotechnology fits in, and that I could teach those subjects and intertwine nanotechnology to give the kids the sense of what's happening now. So the first one I want to look at deals with matter and change, solutions, the periodic table, and even some intermolecular forces, and that will be looking at making nanoparticles. Everyone knows in chemistry class we talk about bulk, silver, and gold. Gold is yellow, and silver is that silver color, or bright gray, however you want to describe it. However, on the nano level scale, gold ends up being red. In fact, I could actually make gold be any color of the rainbow with my students. And silver tends to be a yellow-green color. And so you notice as I get the particle size down, the color changes. So now this, even dealing with just states of matter and physical and chemical changes, I could introduce nanotechnology just by looking at the macro world versus that micromolecular world of nanotechnology. So going back to that first picture, the medieval times picture of making glass. Well, the recipe for stained glass, you need to start off with sand. That is just silicon dioxide. That is the main structure, the backbone for glass. When you make stained glass, or even other glasses, you will add modifiers to it. The modifiers would be normally ionic compounds, iron oxide, sodium carbonate, calcium oxide, for example. All of those modifiers within that sand will lower the workability temperature, the temperature in which I could start molding and shaping the glass. It's also there to add color. For instance, iron oxide. If you ever bought soda lime glass, the cheap picture frames, or pop bottles, that greenish blue tint that you see in the soda lime is actually from the iron oxide color. When you heat up soda lime glass, you will see the sodium flare coming up for all the sodium that is in there. So back in the medieval times, those artists would mix all these ingredients together, heat it up, make it into glass, and start shaping it. But every time they were mixing it and everything, they were scraping the bowl. They were breaking down those ionic compounds to be smaller and smaller and smaller crystal sizes. And what they ended up doing was actually making them into nano-sized particles. And even back then, they were nanotechnologists. For example, in the British Museum, there is the Lycurgus cup. It is a 4th century Roman glass. And the red, nice red color that you see in that glass is due to gold nanoparticles that are found in the glass. The greenish color that you see in the same glass is due to silver nanoparticles. And now you're trying to figure out if that's the same glass, why is it 2 different colors? Well, with this cup, depending on where the light is transmitted from, you get a different color. If it's from the inside, you get to see that nice red. When you shine light from the outside, you see the green color. And there's a research paper that I give my kids, and we'll talk about it a little later on, that deals with scientists figuring out the ratio of how many silver nanoparticles to gold nanoparticles were in that cup. And that becomes then a design challenge for my students in the classroom. So let's get to the basic how to make those nanoparticles. To make silver and gold nanoparticles, all you truly need is silver nitrate with sodium citrate or gold chloride with sodium citrate. Now, you may have seen other recipes for this, and I know some of the original recipes were wonderful, but one of the biggest downfalls of it was you had to heat it up for 30 minutes. I don't know about you guys, but my kids in honors chemistry, regular chemistry, they cannot watch something heat up for 30 minutes. In fact, if something doesn't go on very smoothly, very quickly, they lose their attention, and it's very hard to control in the lab them paying attention to this experiment. So my experiment dealing with these two, I got it down that they could make gold nanoparticles in 10 minutes, and if they want to make gold and silver nanoparticles, it ends up about 15 minutes for both, so that then they can move on in the lab and start analyzing and seeing those properties. So if you look at the picture down below, there's a picture of the red solution. When I add the gold nanoparticles at a small concentration and add the reducing agent of sodium citrate, that allows the particles to go down to a smaller size and you start seeing that red color. However, sodium citrate also acts as a stabilizer. It adds a protective coating around the gold nanoparticles so the gold nanoparticles don't attract to each other and become that bulk gold color that we know of. So sodium citrate is a reducing agent as well as a stabilizer. When you make these, you get that nice ruby red color, and it ends up being a colloidal mixture. So one of the things you could do for solution chemistry is make this and then have a kid shine a laser through it or a light through it, and you will see the beam of light in this solution. That way they know that the particle size has to be larger than what they are described for a solution versus a colloidal mixture. The other thing you could do, I show you that it says /filters. I have the kids use various filters that I attach to syringes to see what size particles they are. And they will find out that even the best filters that I could get through Fisher will not allow that ruby red color to get clogged into the filter. It goes right through. So looking at the pore size of the filters, we then get another idea of how small those particles are. I do then extend it by using a calorimeter or a Spec 20 or a Spec 200, and they start analyzing and seeing what wavelength has the maximum absorption or transmittance, so that they could get an idea of what wavelength of light is being absorbed here. You could also then add salt to this. When you add just normal table salt, sodium chloride, it interferes with that stabilizing technique of sodium citrate, and all those gold nanoparticles start to clump up and aggregate and become larger. So my students now have a blue solution. We could go back and use the filters, and they will find out which filter the blue solution gets trapped in. So they could kind of get an idea of what size those particles are. They will also use the Spec 20 to then look at what wavelength is the absorption for this solution. Now you notice I skipped one thing. I have various beauty products on this slide, and the whole thing is that I like to try to change it and try to connect it to what they have at their house. So they could bring in samples of beauty products, and a lot of them have sodium citrate in it or other anions that will act as a reducing agent. My students will use that instead of sodium citrate in the lab, And they're able to, by changing the concentration, by changing the amount they add, the color of the nanoparticles they make. And in fact, using just household beauty products, my students are able to make every color of the rainbow of gold nanoparticles. We also have taken some of our samples and mailed them off to universities that will then go and do further testing so we could get images of the nanoparticles that we made. By them seeing the color, the wavelength, and looking at the images that we get from universities, my students are then able to research and try to figure out exactly what they made. Other things I do with this activity, sometimes I try to be a little creative, and now Illinois is an NGSS state, so we have some engineering design and some things like that added to the curriculum. So my activity on trying to create their own Lycurgus cup comes into play with the NGSS. They now know recipes for silver and gold nanoparticles, and students have to try to recreate or make their own Lycurgus cup. I have students that try to make one beaker with red solution and a smaller beaker with the silver nanoparticle solution, and they put the beaker inside the other beaker, and a lot of times it works out. They're able to shine the light and get one color, shine the light the other direction and get a different color. We also then talk about stained glass making, and my students are able to make stained glass with their nanoparticles that they make. Some of the recipes that I've seen online and everything have some ingredients that is hard for me to get at my school, for it's not at the company that we normally order from, or it could be just more expensive. The way I do it is that we make our gold nanoparticles like normal, and then I just use PVA, polyvinyl alcohol, one of the key components to making slime, and I add that to my gold nanoparticles. The students then lay them out on cookie trays, or they lay them out in a silicon baking mold or aluminum foil, any of those things. They let it dry. The PVA just peels right off, and you now have a film with gold nanoparticles trapped inside of it. And it mimics that stained glass that the medieval glass blowers made. I like this because if you look in the world, when you sit in a classroom, almost everything is made out of solids. But when we teach chemistry, we teach a lot of gas, we teach a lot of liquids, aqueous solutions, a lot of wet chemistry. Making the stained glass, my students are able to take home that stained glass, and it's now a great talking point to their parents about what they have done in the classroom. Another activity that I do is talking about surface area to volume ratio. And so this is just rates of reactions, or rates of dissolving, rates of absorption. Typically, you see which steel burns faster. I could get a nail, or I could have steel wool. And if I try to light both of those, the steel wool catches on fire a lot quicker than the nail. One of my favorite activities is with polymers and trying to have them absorb faster. Which polymer will absorb faster the water? I buy sodium polyacrylamide. It comes in pellet form. It is known as Soil Moist in the hardware stores, or if you go to other kind of stores like toy stores, science surplus stores, it is your ghost crystals. And I get the pellets. You could buy the pellets in different sizes. I also take the pellets and use a coffee grinder and grind them up and to make powder. And I will grind it up even finer to make a finer powder. I usually end up having about 5 different sizes for my students to analyze. They then add water to it, and they record their observations on the absorption of the water. In regular chemistry, the way I do this to talk about why surface area to volume makes a difference, I make it more edible and fun, and my kids will try to dissolve a Tic Tac and see how long it takes. And then you can get some flat like ribbon candy that is thinner. Try it. That's my two-dimensional type of look. Then they get to see how fast cotton candy dissolves in their mouth. Then granulated sugar, and then powdered sugar. It is another way for students to see how fast something dissolves and what the surface area to volume ratio really has an effect on the overall reaction. To look at it in terms of nanotechnology, I have an activity that is called How Sweet It Is, and that is using blocks, and I've been teaching for over 20 years, at first sugar cubes, which became very sticky. All my students get the same number of cubes, and then they rearrange it to different shapes, and then they're able to graph and see the surface area to volume relationship and what that truly means. So it's another way that they can manipulate and now have a model to see what is happening in terms of surface area and volume. Why is this important? Well, you have to remember, the surface atoms possess the more energy in any bulk material. Consequently, then, that means the surface atoms will be more chemically reactive. They're the ones that are doing that reaction. So nano-sized particles are tiny, that they increase that surface area. So it will enhance that chemical reactivity. One of the examples is that NASA is looking at using aluminum nano-sized particles for their rocket propulsion. And the whole reason why is that those rocket propulsions with the aluminum is more explosive and quicker to react than what they normally have. And I'm sorry for this one typo. It should say super hypophobic, but I guess my spell checker wanted to say hyper. But now we're going to go into self-cleaning applications of nanotechnology. And this would be called the Lotus effect. The Lotus effect was named after the lotus leaf. Lotus leaves, or lily pad leaves, are self-cleaning leaves. You have this great big gigantic leaf that will get dust, dirt, grime from the environment over time. But every time it rains, the water beads up on that lotus leaf and is able to just roll off, and as the water rolls, it rolls all the grime and dirt with it. And so in nature, you can find a lot of these types of substances. Elephant ears, roses, lotus leaves, they all have the lotus effect. Then there are other leaves, as you could see, and that's a leaf from, I believe it's just an iris, that doesn't possess that lotus effect. Even though the water beads up because of hydrogen bonding and high surface tension, it is not as round as you see on the rose petal. If I was able to look at a lotus leaf under a high-powered microscope, an SEM, you would see that there's a bunch of hills and valleys. But on every single hill and every valley, you have a bunch of nano-sized structures, like little bumps on it. For me, I tell my students the best analogy for this type of image would be to look at a strawberry. A strawberry has micro and nano type of structures. It has all those big bumps and grooves, but it also has all those tiny little black dots on it. That type of property is what allows the Lotus effect to occur. If we look at the Lotus effect in this image, you could see the one on the flat, what we think is a smooth surface, our water just beads up like we normally see water beading up. The one on the more jagged hill and valley type of image, the water is more attracted to itself than it is to the surface, so it just beads up. So when you start angling those two slides, the one that beads up rolls right down. The other one slides down. And it's that rolling property that allows all the material to get trapped as it rolls and cleans itself. So you could buy products that have nano materials in it that you could spray on surfaces and create this Lotus effect. In fact, there's a product out that is for glass that you could spray on the glass, and then you will never get foggy glasses in the shower or the mirror to be foggy, or if you wear glasses and you're going in and out of a hot and a cold room, you will never have to clean your glasses. There's also sprays that you could put on cement, on wood, on metal, almost on any kind of structure to give it this effect. In fact, if you look at YouTube, you could find some videos of some of these solutions in Germany that they spray on windshields, and cars could be driving in a rainstorm and not need their windshield wipers because it's just beating right off. The sides or windows that don't have this product on it, you would need a windshield wiper to try to clean it off. So you could put a spray that makes those bumps and grooves to give the Lotus effect, or in the terms of fabric, a lot of your fabrics that are stain resistant use what is known as nano whiskers. And nano whiskers is having that same effect, but it's a woven fiber that is in the material that create little fingers on that fabric. Fingers that you don't really see. And my analogy for those fingers would be that push pin toy that has a bunch of pins, and if you push on it, it pops the pins to make the image on the other side. So all of these products are wonderful, but my students have to analyze things. So I actually bring in various plants for them to test. They have to see whether or not certain plants possess the Lotus effect or not. Then they take one that does and one that doesn't, and they have to do a little more analysis to it. For example, they will start putting dust or graphite. They may put some ketchup on it, and then put some water. And with the inclined planes from the physics department, we start slowly raising that angle so we could see at what point does the water roll off, at what point can it grab all those contaminants, etc. I also have bought a lot of those products that are made for metal or wood or fabric, and we spray it on some clothes or wood, and then we test the treated versus the non-treated. My students then have to look for articles, they read about it, and then they reflect, and they have to become the next engineer and inventor and try to figure out what else can we use this product for. And some of their creativity, their minds, with their creative minds, I get some wonderful ideas out of them. I wish we had the skills to try to create some of these solutions and test things out, but just getting that idea going in their heads sparks some interest. We do try more on a micro scale, add some micro-sized particles to solutions to see if we could get an effect of our own. We also could look at nano waxes and other sprays. Another way I do this is just with microscope slides. I buy some microscope slides, pour some of these sealants on them, and then they put water droplets on it. They have to test it, and then they rank it. They tell me which products actually are showing the Lotus effect, which products did I not really put anything that had the Lotus effect on it, etc. So it's getting them to start thinking and start thinking outside the box and analyzing and using prior knowledge to answer some of these questions. Another area that I use is nanocomposites. And once again, it's another solid. And this is what I like. When I think of a composite, my students know that it's a bunch of material put together. But a lot of times my first year chem students don't realize the reason why engineers and scientists make composites is so that we add these pieces together to enhance or give now the material a property it didn't exist with on its own. And so one of the big areas that nanotechnology plays in is trying to reduce the odor or gas escaping from items. So the use of nanoclays, these are your nanocomposites. They place them into plastic beer bottles and other bottles. I understand for a high school teacher we should not be saying beer bottles, but this is one of the easiest places I could find the samples. You know, a lot of things drive by our alcohol industry. Beer could not be in plastic bottles for a long time because of the exchanges of gases in and out, that the beer became skunky after a while. By putting in the nanoclays, they have a better shelf life and they're able to use it. And in fact, having it in a plastic bottle is a little more safe in an environment than having glass bottles all over the place. You see silver particles added to items, and the reason why silver particles are added is for the antimicrobial effect. Silver-sized nanoparticles like to get rid of the bacteria. We also see nanocomposites as a nanofilm. They place it on pots and pans to give it a non-stick coating. This is another product that now will replace things like Teflon that we have found out some problems with that we used in the past. So looking at the silver nanoparticles. Nanoparticles are there to kill the bacteria. We see them in products such as athletic apparel, socks, refrigerators, plastic containers, and wash machines. Socks and athletic apparel, it's because if you're an athlete, you sweat. When you sweat, a lot of times your feet stink, your clothes stink. Putting in those antimicrobial silver nanoparticles reduces the odor. What happens, though, to the product? Over time, you're going to wash those nanoparticles out, and you're going to lose that effect. For the refrigerator, it's the same type of thing. How many times have you gone into a refrigerator and you could smell the leftover food? By placing those nanoparticles into the lining of the refrigerator, it helps reduce that odor. Washing machines. This one is a fascinating thing that I have my students read about. They read two parts of a story, one on the invention of putting it in the wash machine, and then the other one is the effects afterwards. Washing machines, LG had a line of washing machines that had silver nanoparticles in the drum of the washing machine. If you have a top loader washing machine, you will find out water will just sit in there after a while, and then you get that musty smell. And a lot of people don't like their wash machine tops open, so they always have it closed, and that smell gets worse and worse. By having the nanoparticles in it, they found out they could reduce that smell. However, in today's society, we wear a lot of blue jeans. We wear a lot of pants that may have metal buttons on it or other parts that are metal like zippers and things, and you wash them. Every time you wash your clothes, that metal is scraping the metal. What's happening to those nanoparticles? Well, the silver nanoparticles are slowly getting off of the drum and going into the water supply. Going into the water supply, they go to the water treatment plant, and then because a lot of water treatment plants, especially early on, did not have any requirements to get rid of nano-sized particles, they then just get flushed into the environment. So now it becomes an ethical issue. Is this really good for our environment? And part of the NGSS is argumentative and debating skills. So my students will read all of these types of articles, come up with their opinion, and they would have to debate the pros and cons of the use of nanoparticles. One of the nice things about the silver nanoparticles, it leads to just even telling the students about stories. For instance, that old saying you heard, born with a silver spoon in their mouth. Well, now you could take it to another level. Think about it. Way back when, it was the powerful, the rich, that was able to eat off of gold and silverware. So whenever they ate, every time their teeth would scrape some silver nanoparticles. What was that doing? It was helping them fight off disease. So it was more of the peasants, the poor, that was always ill, but the rich were healthier. To take it to another level with the kids and what they know of is that they see Band-Aids that have silver nanoparticles on it. And so my students do an experiment about that. I went to the biology teachers and they helped me create cultures to grow bacteria, and they will put in a gauze pad that has silver nanoparticles on it, place it on top of that culture. Then we have another petri dish with that culture and just place gauze on it. And then a third petri dish that has nothing. And then the students will then look to see the growth of those bacteria cultures. This will then show them how nanoparticles can help. Nanocomposites are also found in a lot of sporting goods, from hockey sticks to tennis balls to even truck beds. If you look at it, hockey sticks, tennis rackets, all those items that use nanoparticles, especially the multi-wall nanotubes, they will make it that the ball could go farther. They have better strength. They have better flexibility. So you could improve your skills for an amateur. The tennis ball is one of the stories I like, getting back to that diffusion, that oxygen barrier, allowing the air to go in and out. Well, every time you hit the ball and it goes onto the clay surface, it has that transfer of the air much faster. And in fact, if you look at the regulations, they tell you a tennis ball cannot be used no more than X amount of times. With the nanocomposite material inside the tennis ball, it stops that transferring of the gas. And in fact, the tennis balls then last a lot longer. Here's another interesting thing to argue and debate, because the company that came up with that, after a while, took it off the market. And the main reason why wasn't because it was a bad product. They found out more and more people weren't buying tennis balls. And so I now have the kids thinking about business and what's good for business versus what's good for a consumer. When you look at the truck bed is very similar to someone who's wearing shoulder pads and everything else. By placing those nanocomposites in there, you make it lighter, you will have it stronger, you have it tougher, and that will then lead to more cost-efficient, more aerodynamic when it comes to things like buying gas and everything. For shoulder pads, I love sports, and I know when I helped out with football, there were athletes back in the late 80s, early 90s, who would have neck injuries, so they would have to have the shoulder pads that had the neck protection on it, and the shoulder pads weighed a lot. Now, by putting in nanocomposites and multi-wall nanotubes in there, the shoulder pads are lighter but still have the same effect of being stronger and tougher and more resistant. So activities that I do with nanocomposites: one, I could do impact testing. My kids will either bring in different samples of plastics, or I have samples that I know what they are. We then raise a plumber's bob up different levels, drop the bob, and see what kind of impact it has on the material. We will also bring in things that have nanocomposites in it, and then they compare how durable one is to the other. For silver nanoparticles, we already talked about that. And then construct composites. We could do it more on a macro or micro scale world than a nano world in my classroom. But for instance, you could just make plain old silly putty, or GAC, whatever you want to call it. That is white glue and borax. And then you can make GAC and add something like calcium carbonate, chalk. When you add ground chalk to it, you will find out that the properties of that material drastically change, then from having a fun, silly putty-like substance to having something that will also pick up pencil. It will pick up newspaper ink. So it now enhances that property. If you want to bring in things like the beer bottles that have the nanocomposites, I have hooked those up with altering the cap and adding a bicycle pump nozzle to it. I add then my pressure sensor that I have from Pasco, and I know Verniers pressure sensor will work just as well. And I will then be able to measure what is happening to the gas pressure inside the bottle over time. We could also add oxygen sensors to it, and we could then measure the oxygen transfer over time. Looking at the time, I'm going to go quickly on these next two because I have so much to tell you. I really love talking about this stuff. Another ethical issue is nano substances in cosmetics. How many of you guys saw people back in like the 80s, the 70s that are lifeguards and they have that white stuff on their nose, zinc oxide? Those lifeguards loved zinc oxide because it protected them from the sun. Now with nanoparticles, nano-sized zinc oxide is colorless. So someone could put zinc oxide on their nose and you can't really tell. Well, one of the first things you could do is get UV beads and a bunch of different sunscreens, and you could test how effective are those sunscreens. But to turn it into an ethical issue, then start talking about what size particle can be absorbed into your skin. What could that be doing to your skin? What could that be doing to your body? I have students that start researching and figuring these out. And in fact, 2 kids, it led to a research study of what they wanted to do when they went to college, just by intriguing them in my sophomore level honors chemistry class. The last one is the connection truly to biology, and that is drug delivery. A lot of medicine wants to get specifically targeted to a certain area. They want it to be time released. We want it to kill the right kind of cells. And so there's many advancements with nanotechnology and drug delivery. There has been research done on trying to put things like nano-sized iron type of filings, magnets, into the medicine, let it go, get interacted, trap with the toxins, and then you could be wearing a device on you, and all those toxins that are now attracted to that nanoparticle will get attracted to the magnet that you're wearing, maybe on your wrist. There has been other research about trying to target a certain kind of cell to simulate that normal cells and abnormal cells do not behave the same way. You could get something as simple as store-bought Jell-O already made versus the Jell-O that you make at home. Get those two, put it in a container, put a sunlight on it, a heat lamp, and you will find out that both Jell-Os don't start losing their shape at the same time. So because they are made somewhat differently, they behave differently. The one that I want to talk about is really the time release of drug medicine, and that is going to be dealing with cation exchange. With cation exchange, I am going to use sodium alginate. What is sodium alginate? Sodium alginate is found in brown seaweed. It is a food thickening agent. You find it in ice cream, jellies, jams. Gaviscon has a lot of sodium alginate. And if you mix it with calcium chloride, you could get these little BBs. The chemical interaction that is occurring is that sodium alginate is a long linear polymer with a bunch of sodiums attracted. When you put it in the calcium chloride, it does a cation exchange. It exchanges sodiums for calciums, and it links them together. So how do I make my medicine? I will have the sodium alginate solution in my syringe, and I will also make sure I dye it maybe red or blue, some kind of color. Then, with my ring stand and clamp, I will change the height at which the syringe is at, and I will press and drop those little BBs into the calcium chloride. That way I make my sodium alginate BBs. By changing the height, I could change the size of that BB. I could even add a little needle to it, and I could even make them even tinier. So here's some pictures of me just doing it at my house, making little BBs so you could see what they look like. Now for the medicine part. So I have this food coloring with the BBs, and I make it into the solution. I'm now going to transfer those BBs into a Petri dish that has water. Now it's diffusion. That red food coloring is going to diffuse out over time. My students then decide what their time intervals are going to be. They wait that time period. They pour the liquid out, put it in a Spec 20, and measure the absorbance. They put the water back in, time it some more, and they keep doing it so they could see how much medicine, in this case red food coloring, is getting to the body. They do this procedure for multiple sizes of BBs. Some large BBs, some tiny BBs, and they get their data. Their data ends up looking somewhat like this. And I'm sorry I picked all the graphs that didn't have numbers, labels on it, but you have time on the horizontal, and up on top would be how much it's been diffusing out. So if you look at the one over here, the single picture, that graph shows you the different sizes and how it diffuses. And then some students try to change how much sodium alginate they actually use. And they notice that it doesn't matter how much thickening agent, it all behaves somewhat the same. It is really a size-dependent problem. How do I link this then to medicine? I come in and I said, I got a request from a doctor. And they get a little schematic, a graph, and they go, they need medicine that will do this kind of profile. Maybe it's like the black line you see in the lower graph there. Maybe that's the profile they want. So now it's up to my students to look at their data on what the different size particles actually did. And now they have to come up with a mixture of those particles to get the right profile that they want. This is now making them think outside of the box, making them apply what they just learned, and now linking it to something that they see in the real world. And it makes then this concept in nanotechnology more prevalent in their minds. So with those few ideas, I highlighted matter and change, scientific measurement, the atomic structure. I didn't even highlight, but we can link it to the periodic table or bonding. I forgot to highlight bonding with the intermolecular forces, solutions, and rates of reactions. And I do have, for all the other topics, other examples if you want. Hopefully, with these ideas, you have seen some areas that you could put nanotechnology in. I still teach my normal class. I still could cover all the same topics, but now I make it a step further and having them connected to things that they see in real life, they hear about on the TV, or they see it in the movies. I do want to take this last minute or two to thank the Northwestern University, first of all. They're the ones who started me off on nanotechnology by allowing me to do an RET experience. If you've never done an RET experience, you may want to look at it. I know that there are a lot of universities that do it in nanotechnology, and it's a great experience to get to see what research is out there, be able to use the latest equipment. I was able to learn how to use a SEM, a FIB SEM, a TEM, all those pieces of equipment that I never got to use in my undergrad at all, ever. They're the ones that inspired me because I was able to look at using nanocomposites in fireman clothing. I was able to work on solid oxide fuel cells, art preservation. If you want to know about nanotechnology in the art world, I have some great ideas for that. So they actually made me springboard into wanting to learn more and trying to put it into my classroom. I also want to thank the Material Worlds module that came out of Northwestern. They allowed me to do an internship and work on a lot of these activities that I was able to make my own. The Polymer Ambassadors for supplying me the polymers and things like that, as well as AACT, which is now a network for chemistry teachers that have now linked me to industrial people that also work in the field of nanotechnology. So now I have a bigger network to go to, and especially nano.gov for allowing me to speak tonight and all those wonderful resources that they have. You know, if you haven't gone there, you should really check out what they have all to offer. They have a lot. And then last but not least, I want to thank all of you for listening to me and listening to all my ideas. I do want you to know if you have any questions or if you really want to see my activities and get copies of them or get copies of the articles that I use in my classroom, please don't hesitate. Just contact me at Sherri Rukes. I have 2 email addresses there, sherri.rukes@d128.org. That is my work email. Or you could contact me at lovechem@gmail.com. Please note, when you email me and you want these activities, I would love you to just email me your address. I do have a lot of information to give you, and some of them I did get permission to use in the classroom, but not to post it online. And so I wouldn't mind. They told me I could share it with anyone else who would love to use those articles in their classroom. But by doing it by email, I'm afraid that it's easier for some of you to just put it out there online. So please let me mail you the CD full of information. So thank you again, and I hope you guys thought it was interesting.
Sherri, thank you so much. I found it interesting, and it's the second time I heard it. So everyone who's been participating, I forgot to mention at the beginning, you're welcome to ask questions. There's a questioning pod off to the side. And Sherri, I'm glad you mentioned that you'll send out the CD, because that was one of the questions I wanted to ask you, was if there will be a way for everybody to get some of the information that you mentioned. Thank you so much for that. And since this will be archived, you'll be able to see this information up on the nanotube too once we've got it all posted. I also wanted to point out that the resource portal that I mentioned at the very beginning has the molecular world modules on there, so that's an easy way to find those as well. And one of our previous webinars mentioned remotely accessible instrumentation for nanotechnology. This is an NSF-funded program. It's free. You can check it out. It's on nanoforme.org. And when you were talking about the Lotus leaves, that's exactly what I thought of. It's a program where you can actually contact them, and they'll set up a time for you in your classroom to remotely access something like an SEM. So you could send them in a Lotus leaf, and your students would be able to see it. So I wanted to let everybody know about that as well. And it was great. I loved the Lycurgus cup. I wish my chemistry teacher did that when I was in school. So does anybody else have any questions? Doesn't look like it, just lots of thanks. And I think that'll be it. I wanted to thank again, oops, sorry, wrong way. I wanted to thank you all again for joining. Oh, go ahead.
Quinn, I'm going to jump in. I just wanted to make sure that you let everyone know that this is going to be archived on nano.gov. So please share the link with your colleagues. I think this was just a tremendous amount of information, and we want to make sure that those who are not available to attend tonight will still be able to benefit from the great information that Sherri shared tonight.
I know we're out of time, but we just got one really quick question, really good question, actually, Sherri. If you can answer it quickly. I don't know, maybe it's not, but I thought that was a pretty great question about getting your administrator to agree to do all that great stuff in class. Was that an issue, or was it similar enough to what you usually do in a chemistry class that it wasn't an issue?
everything that I do in my classroom has a traditional chemistry lab type of thing, and we are allowed to pick and choose what labs we want to do at times, and I just need to get to point A to point B every semester, and so as long as I could get to the same point everyone else does, I'm allowed to pick and choose how long I spend on one subject versus another. Um, I'm the crazy one at my school because I like trying new things, um, whereas there are people who are more wanting to be the traditional, oh, this always has worked for me. But now I've noticed more and more are interested because Illinois is an NGSS state, and we have that argumentative portion, that more inquiry type of portion, that engineering design portion, and making more scientific questioning coming up, that a lot of this then leads and lends itself right to the NGSS. So I think at first for me, I didn't have a problem, but now I think more are willing because of what we have to do in the classroom.
Wow, that was a great answer. And everybody online seems to agree. With that, since it's the evening and you're all busy, Sherri, thank you again for giving the webinar, and everyone, thank you for participating, and I will send out a link once it's all up and archived. So good night.
Good night, and thank you, everyone.